Okay, so now we're going to talk about resolution in measurement. So when you talk about resolution, you often think, or at least the first thing I think of, are TVs. And we have Ultra HD 4K down to HD 1080p. And so this is quite useful for us to think about what do we mean by resolution. Well, simply put, that the higher the resolution, the more information that's going to be contained within a particular cell. So on the left here, for the same size, so we have maybe a square. Let's go here. We have 9 boxes of information, whereas on the right, we've only got 1. So we're going to have more information contained within a higher resolution output. So we can see this clearly. We've got 300 dots per inch on the image on the left here. That basically means pixels when we talk about digital imagery. So we've got 300 pixels per inch of this image. And on the right, we've got 72 pixels per inch. And you can quite clearly see that the image on the left is much clearer, much crisper, contains a lot more information. It's more accurate. It's more accurate to real life. And then on the right, it's lost a lot of information. You have to kind of squint to sort of see what it is. And this is true of sensors as well. So the first thing that you need to think of is, what do we mean by resolution? Well, when we talk about measurements, it's the smallest detectable value in a measured parameter. So what do you think the resolution of this ruler would be? Well, the smallest detectable value would be these individual divisions. And we have 10 divisions for each 10 millimeters. So we can say that each division is 1 millimeter. And when we're measuring, we generally round to the nearest millimeter. So we can say the smallest detectable value in this ruler is 1 millimeter. And this value is fixed. So here's an example. We usually say the full scale resolution. So here's a force sensor that measures pressure or force in newtons. And this particular one, its range is 0 to 150 newtons. And it says that the resolution is 0.1% of its full scale. So what is the smallest measurable change in force? I.e., what is its resolution? Well, we do 0.1% times its 150 newtons, so its upper range, and we have 0.15 newtons. So its resolution is 0.15 newtons. So for digital multimeters, we have kind of a lot of things going on in this. We have 2 different resolutions. We have its ADC bit resolution, that's its analog to digital converter. And we also have the display resolution. So when we talk about resolution of digital multimeters, often what we're saying is this display resolution. But we have to take into account particularly when we're designing digital multimeters, we kind of have to take into account this ADC. And this is true for oscilloscopes and other measurement instruments like this. So digital multimeters, they consist of inputs and outputs, analog to digital converters, microcontrollers, processors, measuring circuits, and the display. What it does is you take your test probe, and what you're doing, an analog signal is usually passed through it, a voltage over a resistor, for example. The analog to digital converter is then going to sample these points along these points in time what the voltage is at any one point, and it's going to approximate that voltage into a binary number, and then it's going to convert that into a decimal number that we can interpret on the screen. So here we go, this is the analog to digital converter. So we have 1 volt, an analog signal of 1 volt, and at each sampling time here, so we've got evenly spaced samples, it's going to capture this at regular intervals, and what you see, this is a digital signal now. It's kind of like a staircase signal. It's going to sample it, hold it to the next one, sample, hold. So for example, this is the analog voltage across a resistor, and this would be the output waveform, or the input waveform, sorry, that we're getting across the resistor. A nice sinusoid. And this has infinite resolution, because if we were to zoom in, ideally zoom in as far as we can go in this, there would be no discernible or detectable intervals there. It would just be continuous. So we can say analog signals have an infinite resolution. However, the ADC, what it does is it snapshots, as we said, and it converts this into a digital signal. It represents it as a string of ones and zeros. And how close this is to its captured signal all depends on the quality of its ADC. So if we have an 8-bit ADC, then what we're going to have is 256 divisions in the 0 to 1 volt range. So what we've done is we've divided 1 volt by 256 divisions. And to get this number, you do, for binary, you do 2 to the power of n, where n is 8. So 2 raised to the power 8 is 256. 16-bit ADC, well, that's going to have 65,536 divisions. And so the ADC resolution, or the step size, is here. We can see that for the 8-bit, 3.9 millivolts would be the resolution, and 15.3 microvolts for the 16-bit. So you can see, even just by doubling the bit size, or the bit depth, you have a dramatic increase, a dramatic improvement in resolution. So what about the resolution of the meter itself? When you have specs, it usually says the resolution in terms of the LCD display, or I shouldn't say LCD display because D does mean display, the liquid crystal display, the LCD. So the smallest value the display can show would be the resolution here. So here the resolution is 1 millivolt because we have the decimal point here, and it's 19.999, and this can increase by 0.01 volt each time, or 1 millivolt each time. So we say that this resolution would be 1 millivolt. So let's put this into some kind of context, an example. So say we have an analog to digital converter, and it's an 8-bit processor, and it's used to convert DC voltage between 0 and 5 volts. So whatever our application is, we're wanting to measure 0 to 5 volts. And the output of this ADC is given as a binary number, 00101100. And what we're asked to do is find what that voltage is. Okay. Well, first of all, what do those numbers mean? And if you're not familiar with binary, then I'd recommend doing a little bit of research on that. But here we have the least significant bit on the right here, and we increase in significance. So we say the most significant bit would be 2 to the 7 is 128. So this represents 128 here. So we can have, this bit can mean 0 or 1, this bit could mean 0 or 2, this could be 0 or 4, and so on. And if we add all them up, what we get is the maximum number is 255. So it can display, or it can output numbers of 0 to 255 in decimal. And what we're trying to do is convert that into translate that for 0 to 5 volts. So what we do is we've got 5 volts, and we're dividing that by 2 to the 8, which is 5 divided by 256. And the resolution of this ADC is given as 0.0195 volts, or 19.5 millivolts. So to go on and calculate what the voltage is, so this is what happens in a processor. This is what a processor would do. It would take those strings of zeros and ones. It has a resolution. It knows what the correlation is between the resolution and the zeros and ones, and it converts it into a voltage that we can understand. So this is what it's doing, essentially. So this is our binary string. And what we're doing is we're adding these up. So we're multiplying these. So 128 times 0, well that's 0, that's 0. 32 times 1, 32, plus, well that's 0. 8 times 1, 8, plus 4, and that's what we're doing. So 32 plus 8 plus 4 is 44. And what we're doing, 44 times the resolution, 19.5 millivolts, and that's giving us 858 millivolts. So the reading would be 0.858 volts. So have a go at this. Try this one. If our digital multimeter display resolution is 1 millivolt, on the 1 volt range, what ADC bit depth would we need? So what it's asking us is we've got 1 millivolt. Well, I've actually put 0.1 millivolt there, but let's say this is 1 millivolt, the resolution, on the 1 volt range. What is the bit depth that we need? So what it's saying is what ADC do we need? Do we need a 4-bit ADC? Do we need an 8-bit ADC? Etc. So here's the solution to that. So the desired resolution is 1 millivolt. And so we can say R is equal to 0.001, 1 millivolt. And we know that the resolution is equal to the voltage, the range of voltage, divided by 2 to the power of n, and that is the resolution. So we can rearrange that. We got R is equal to 1 over 2 to the n. So 2 to the n is equal to 1 over R. So we've rearranged that to get 2 to the n. And now what we want is we want n. We're looking for n here. So if you're comfortable with your exponentials and logarithms, we take the log of both sides. So log 2 to the n is equal to log 1 over r. And what we do to rearrange that for n, so we transpose this for n, we've taken the log of 2 over to this side, and n is equal to log 1 over r over log 2. So plug in our resolution for r, and what we've done, we've got, this is 1 volt, and it comes to 9.97. So a 10-bit ADC would be the most suitable for this application. And that's the kind of ADC that we'd be looking for.